Hello, my name is Ann Watson and I am a junior studying electrical engineering at the University of Missouri. Today I will be presenting on an automatic detection for buffer overflow vulnerabilities on ARM processors using grammar sets. So, some background on ARM processors. ARM stands for Advanced RISC Machine and is a family of reduced instruction set computing or RISC architecture for computer processors. And as of 2021, over 200 billion ARM processors have been produced. These are used for smartphones, laptops, tablet computers, streaming devices, and other devices due to their low cost, minimal power consumption, and low heat generation. ARM is the most widely used instruction set architecture. For this study, we use C to examine different functions. During compilation, C is translated to assembly language. Assembly language is faster and necessary for performance-critical codes. As stated in the title, this study focuses on buffer overflow vulnerabilities. A buffer is defined as a reserved segment of memory within a program that holds the processed data. If the entered data is longer than the intended size of the buffer, it will overflow into different areas of storage. C is particularly vulnerable to this because it does not have any built-in error checking. When programs have buffer overflow errors, there is potential to overwrite the ARM processor stack pointer and direct it towards malicious code or change the behavior of the program. In 2021, the report from CWE said that the buffer overflow errors are listed as one of the most dangerous software weaknesses in computer security. According to the National Vulnerability Database, buffer overflows are one of the most common vulnerabilities found in applications. C and assembly are particularly vulnerable to cyber attacks due to their lack of built-in error checking. The overall goals are as follows. First, to examine the assembly code of different vulnerable C functions. Next, we aim to identify potential buffer overflow errors within the vulnerable C function assembly code. Then, we looked at the secured versions of these C functions and determined the patterns that protect the secured functions from buffer overflow errors. In order to accomplish these goals, the article that OWASP published on specific vulnerable C functions was used. The table shows the different vulnerable C functions, their secure counterparts, and a description of the goal of the function. For this project, we used gets, string copy, and string cat to observe their behaviors. The source code for the C functions was obtained from the GNU C library. The first function we will look at is the secure fgets function, which retrieves a string. Then we will look at the unsecure gets function. The first highlighted line of assembly code stores the value of the size of the buffer into the memory address that is an offset of -28 away from the frame pointer. This is helpful to know as we follow through the rest of the code. The second highlighted box is where the assembly code branches to the getLine function, which gets the input string, puts it in the buffer, and returns the amount of characters read in. This count is then stored into a -16 offset from the frame pointer. The third highlight demonstrates the bounds checking. The assembly loads in the size variable and the count variable and then compares the two. If the count variable is larger than the size variable, it branches to printf and prints an error message. When looking at the vulnerable gets function, we look to see if there is ever a comparison between the size of the buffer and the input string. The first comparison highlighted in the assembly code is only looking to compare the character read in with an end of file value. The second comparison line is checking to see if there is an end of file character at the start of the string. The third comparison line checks to see if file end of is true, and the last comparison checks to make sure the character is not the new line character. There are no bounds checking in this gets function, meaning any string could be input and potentially overwrite the stack pointer, hence a buffer overflow error. The next function we looked at was the secure string end copy function. This uses different types of bounds checking as seen in the highlighted box. It loads in the size of the buffer, then subtracts 1 from that, and then stores that back into the memory location that holds the size. It then compares that with 0, and if it's not equal to 0, it branches back up to load another character in. The buffer size essentially acts as a while loop counter, and once it is subtracted down to 0, it breaks the loop and stops reading in characters. We can now look at the vulnerable string copy version. The only compare statement the assembly has is ensuring that the character read in is not a null character. There is no bounds checking otherwise, and leaves it open to attack. The final function we will look at is the string concatenation function, string cat. This function uses secure functions within it that require the buffer size input. For example, it utilizes string length to retrieve the length of the input, and this function accepts a maximum length parameter. It also uses memcopy, which requires a maximum length parameter, as you can see in the second highlighted assembly box. The first string, second string, and size of the buffer are loaded into the registers to pass to memcopy. The vulnerable string cat does not have a size parameter and uses two vulnerable functions, string len and string copy. Additionally, at no point in the assembly code is there a comparison made. The first initial observation made is that there are three different forms of strategies for input validation. The first one was observed with fgets, which was using an initial check to see if the length of the string entered in is longer than the maximum size provided. The second form was observed in the string and copy function, which used the maximum size variable as a decrement or increment while loop counter. The third form was using secure functions within that require a maximum length argument to perform bounds checking. There were also some other observed patterns. First, it was observed that a single line of code is not sufficient for buffer overflow vulnerability patterns. For example, each defense technique requires more than one line of code. The second observation was that a subtract or add assembly operation paired with a compare to 0 that is being used functionally as a while loop counter could be considered a buffer overflow error checker. Next, as seen in the fgets function, a compare between two registers which each have a value of a length in them could signal a buffer overflow protection. Next, calling a function that gets the string or input's length, for example, string len, could signal buffer overflow protection. Finally, using a variable that contains size information or comparing the length of an array to another number could also be signals. This project is still actively in progress. We are now working on a tool that will implement a parser that scans the assembly code for the patterns mentioned on the previous slide. Then, a defined assembly grammar set will be integrated in the tool for vulnerability detection. In order to evaluate the results, we will use three different measures: recall, precision, and f-measure. The goal is to have a recall of 1, which would indicate no false negatives, which are a type 2 error. Some threats to the validity of the project are as follows. An external threat is that so far this project has only been ran on 6 functions, or 3 pairs. An internal threat is that the tool algorithm is modular, meaning it is only checking if the function itself has any implementation of a buffer overflow error protection, but disregarding if other functions that are called are implementing the error protection. These are some related works to the project. The VCM detection is specifically for ret2zp, which means there is no input of malicious code. A attack exploits a stack buffer overflow to redirect control flow to a function present on the system and to control the arguments to that function. Redirecting control flow can be performed directly by overwriting a return address on the stack with the address of the desired function. The rest of the related work is mainly for C and C++. Future work. We first aim to define a buffer overflow vulnerability grammar set, which will then allow us to move into a text-based machine learning algorithm. Utilizing RNN recurrent neural networks, we will then create a model that automatically detects buffer overflow vulnerabilities in ARM assembly code. Thank you very much.